So let's start combinational circuits. So in combinational circuits, we will be seeing half adders, full adders, multiplexers, demultiplexers, encoders, decoders, comparators, etc. Okay, so let's look at the first combinational circuit. So the first one is half adder. So in this case, what we do, we add two 1-bit together. So let's say A is 1 bit, B is 1 bit, and this is my half adder, and I will give a sum and I will also give a carry. So let's say this is my carry. So if I make the truth table of this half adder, I have A and B here, I have S and carry. So 0 0 0 1 1 0 1 1. So if I add 0 0, my sum is 0 and I don't have any carry, my carry is 0. If I add 0 and 1, my sum is 1, my carry is 0, right? I don't have any carry. If I add 1 and 0, sum is 1, carry is still 0. If I add 1 and 1, sum is 0 and I have a carry, right? So this simply what we did, we summed these two or these two and these two, right? So we just added these variables. So what is the function of S? So how can I write the function of S? So I need to look at these two ones here. So it is either A naught B or A B naught. So what is this? This is an XOR function, right? A XOR B. So this is my function for the sum in the half adder. So what is the carry? So carry is 1 if A is 1 and B is 1. So this is the Boolean functions for the half adder. Okay, so this was the half adder. Let's look at the full adder. So in the full adder, instead of 2 inputs, I have 3 inputs, A, B and carry in. And again I have sum and carry out. Okay, so this is my full adder. If I write my truth table, I have A, B, carry in, sum and carry out. So I have all possible inputs. So my sum is for each case. If I have 3 0, my sum is 0, my carry out is 0. 0 0 1, my sum is 1, carry out is 0. 0 1 0, sum is 1, carry out is 0. 0 1 1, sum is 0, carry out is 1. 1 0 0, sum is 1, carry out is 0. 1 0 1, sum is 0, carry out is 1. 1 1 0, sum is 0, carry out is 1. And if I have 1 1 1, my sum is 1 and my carry out is 1. So given this truth table, we can find the function for S for the full adder and function for the carryout for the full adder. But we can also use Karnaugh Map to simplify these, right? So let's draw our Karnaugh Map. So let's do this for the sum first. So I have a 1 here, 1 here, 1 here and 1 here. So this is a very interesting Karnaugh Map. I cannot make any grouping. So I have to write each one individually. So this is A naught, B naught, carry in. And this is A naught, B and carry in naught, and this is A, B naught and carry in naught, and this is A, B and carry in. I can write my sum function as A naught, B naught, carry in, or A naught, B carry in, or A, B naught, carry in, or A, B and carry in. So this is actually sufficient. So, but if you write this shorter way, this is equal to carry in XOR A XOR B. So let's see how I can get this. If I take carry in out, so this is like A naught, B naught, or A, B, or then I can take the two terms to the carry in naught parenthesis. So this will have, we have this here, we have this here. So this will be A naught, B, or A, B naught. So as you see, this is A XOR B and this is A XOR B naught. So in a way, you have a variable here and you have a not of that variable. So, and then you see we have carry in here and then we have carry in not here. So then what you can write, this is actually carry in XOR A XOR B. Right? So this is how you can get the short Boolean expression for this sum. Okay, let's look at how we can find the carryout, right? So let's do the Karnaugh map for the carryout. So for the carryout, we have one here, one here, one here, and one here. So I can make one group here, and this is B carry in, another group here, and this is A and B, and another group here, and this is A and carry in. Okay, so carry out is given by A, B, or A carry in, or B carry in, right? So this is our carry out function. Okay, now let's do an example. So in this example, we are asked to design a full adder using 2 half adders and 1 additional gate. So this gate could be inverter or NOT gate, and or NOR, etc. Okay, so what we are trying to do is we are trying to design a full adder using 2 half adders and 1 additional gate. So let's say this is my full adder, and I have inputs A, B, and carry in, and my outputs are S and carry out. But inside this I can use 2 half adders. So this is first half adder, and let's say I have another half adder here, and then I have 1 additional gate, and I don't know what is it. This half adder has 2 inputs and 2 outputs, right? And now let's try to do the connections. So I can connect A here and B here. I have sum here and carry out for this half adder here, A and B for this half adder, A and B for this half adder, and sum and carry out for this half adder, right? So what will I get here at this port? This is half adder. I will be getting A XOR B, and here for this carry out I will be getting A and B. So what I am trying to do, I am trying to get this S, and this S should be, let me write that S again. S is equal to C in XOR A XOR B. So I got one A XOR B here, and I have my carry in here. So if I do this, if I connect this A XOR B here, and if I connect carry in here, so what will I get here? I will get C in XOR A XOR B. So I can connect it here. So now I got my sum using 2 half adders. So my carry out here is A, B, or A carry in, or B carry in, right? So I have A and B here. So I need this A carry in or B carry in, right? So what do I have here at the carry output of the second half adder? I have carry in times A XOR B. So I have these two, right? And then I am trying to get this output. So let's see how can I get those outputs. So let's write the truth table for this. What I am trying to get is this carry out, right? So the carry out is, it is 0 0 0 1 0 1 1. So, and let's see, if I have A and B here, I will have 0 0 0 0 0 0 1 1. And if I have carry in and A XOR B here. So this is this term and this is here. So for this, if carry in is 0, then this expression will be 0. So I have 0 here, 0 here, 0 here, and 0 here. So this carry in is 1. I need to look at XOR of A and B. So this is 0. If carry in is 1, XOR of A and B, this is 1. If carry in 1, XOR of A and B, this is 1. If carry in 1 XOR of A and B, it is 0. Now let's see. So I am trying to get 1 here, 1 here, 1 here, 1 here. So this is I can get from here. This one I can get from here. And these two ones I can get from these two ones. So in a way, if I OR these two expressions, then I will be getting carry out, right? So it means if I put an OR gate here and I take one input from here and another input from here, I will be getting my carry out signal, right? So this is how we can implement the full adder using 2 half adders and 1 additional OR gate. Okay, now let's design a mid parallel adder from 1 bit full adders. So what we are trying to do, so we have a variable A, and this is a 4-bit variable A3, A2, A1, and A0, and I have another 4-bit variable B, and this is B3, B2, B1 and B0. And I would like to add these 4-bit variables, and I will get S0, S1, S2 and S3, and I will have a carryout in this case. So this is called n-bit parallel adder, and I am trying to implement these circuits using 1-bit full adders. So in this case I need to have 4 1-bit full adders. So this is first full adder. Let's say this is full adder 0, and I have A and B here. Let's say this is my carry in, and these are my S and carry out. So this is another full adder. Let's say this is full adder 1, and we have carry in here, we have S carry out, A and B here. So these are my 4 full adders. So this is full adder 2, this is full adder 3. Okay, now I need to do my connections. So I will be connecting A0 here, B0 here, and initially I don't have any carry in. I can put a 0 here, and this will be my S0, right? So this carry out, I do this addition. If there is any carry out, I need to take that carry out from here, and I need to add it to the next section, right? So this carry out will go to the as the input to the next adder stage, right? So I will have A1 here, B1 here, and I will get my carry in from the previous stage carry out, and this will give me S1. And if I have any carry out, this needs to go to the next stage carry in, and this will have A2, B2, and I will have S2, and this carry out will go to carry in of the next stage, and I will have A3 and B3 connected here, and this will be my S3. And this carry out will be my carry out for the sum, right? So this will be equal to this carry out. So this is how we can implement a 4-bit adder using full adders. Okay, so let's continue. Let's try to implement a subtraction circuit using this adder. So let's say I need to have A3, A2, A1, A0 here, B3, B2, B1, B0 here, and I need to do a subtraction operation. So how can I do the subtraction operation using the same circuit? So what I am trying to do, use the above circuit to do subtraction as well. So we can add some additional gates to this circuit, then we can get a subtractor as well. So this subtraction operation is equal to A3, A2, A1, A0, and then instead of doing this subtraction, I can take 2's complement of this variable. So what I can do, I can have B0 not, B1 not, B2 not, and B3 not, and then this is the 2's complement of B, right? So now I can do the addition. So this will give me again S0, S1, S2, S3 and carry out 0. So what I need to do, I need to make sure I can do this operation in the above circuit, right? So let's say I have a variable M. So let's say I have a variable M. If M is 0, above circuit will do an addition. If M is 1, it will do subtraction. So if M is 0, I will be doing A plus B. If M is 1, I will be doing A minus B, right? So to take care of this one here, I will be using this M variable, okay? So what I will be doing, instead of 0, I will be connecting this now to variable M. So if this M is 0, I will be doing the A plus B. If M is 1, I will be doing A minus B, right? So now I take care of this one, and by using this M variable, I can either take it 0 or 1. But now I have to take care of this, right? So these variables, so these 4, if M is 0, I will be getting B3, B2, B1, B0. But if M is 1, I should be getting B3 not, B2 not, B1 not, B0 not. Right? So I have to add some modification here to implement this. Right? So how can I do this implementation? Let me erase this portion, and I am trying to implement something on these inputs such that if M is 0, I will be getting B3, B2, B1, B0 directly. If M is 1, I am getting the NOT of these bits. Okay, so what I can do, I can have an XOR gate here. So I am adding an XOR gate here, okay, for all of them. So what this XOR gate will do, depending on M, it will either directly pass the inputs or it will take the NOT of my inputs. The first input, I will connect them to the M variable, okay? So this M variable is driving the first input, and then the second input, and I will be putting B0 here, B1 here, B2 here, and B3 here. So this is my M variable. The first one is M, right? This is M, 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 M. So in an XOR function, if M is 0, then I will be getting here B3, I will be getting B2 here, I will be getting B1 here, and I will be getting B0 here, right? And if M is 0, I will be doing here A plus B if M is 0, right? So let's see what will happen if M is 1. So if M is 1, if I XOR something with 1 or B3. Let's do this here. Let's say I have an XOR operation on X and Y. Let's remember it 0, 0, 0, 1, 1, 0, 1, 1. So this is X XOR Y. Right? If you look at the result 0, 1, 1, 0. So if I XOR X with a 1, what will happen? If this variable is 1, right? This is these two cases. If X is 0, the result is 1. If X is 1, the result is 0. So if I XOR something with 1, the result is NOT of X. Okay. So this is basically inverting my first variable, right? So this is the inside the XOR case. One of the inputs is 1, which is Y, right? And then if X is 0, my result is 1. If X is 1, my result is 0. So it means if I XOR something with 1, I will be getting NOT of that variable. So in this case, if M is 1 here, so I will be getting B0 NOT, B1 NOT, B2 NOT, and B3 NOT here. And for this carry in input, I will be getting 1. So basically, if M is 1, this is what I will be doing. And I will be doing actually a subtraction operation. So using this circuit, the 4-bit parallel adder and then adding 4 XOR gates, and using this M variable, I can have a circuit which can do addition and subtraction at the same time. So this is a flexible circuit. It can do either subtraction or addition depending on value of this M. Okay, now given this circuit, the same circuit, let's try to add an overflow detection for this circuit, right? So how do I add an overflow detection here? So let's do an adder here. Let's draw it again here. This is S0, this is S1, this is S2, this is S3, and this is my carryout. So these are full adders. So, and I would like to add an overflow detection circuit to below 4-bit parallel adder. So how can I implement this overflow detection circuit, right? To detect an overflow, we need to write a Boolean function, right? Let's say I have an overflow function OV. This is high if A is positive and B is positive and S is negative, right? So this is one condition for the overflow. And another condition, or if A is negative and B is negative and S is positive, right? So if I am adding two positive numbers and the result is negative, or if I am adding two negative numbers and the result is positive, then there is an overflow. So how can I express this in Boolean? So what is the condition for A being positive? Okay, if A is positive, it means A3 is 0. Then I need to write A3 not. And B is positive, it means B3 is 0, right? If B3 is 0, B is positive. So I will say B3 not, and sum is negative. If S3 is 1, the sum is negative, then I will say S3. So this is one condition. Or A is negative, it means A3 is 1 and B3 is 1, B is negative and S is positive, S3 is 0. So this is my condition, right? So what I need to do, I need to add some gates here. So basically, if A3 is 0 is not of this, B3 is 0 and S3 is 1. Let's take this as well. Okay, now I will be deleting this portion. Or I will be getting A, B and not of S3. And then I will be ORing these two. And this is my overflow function.